Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
A block of ice is rotating on ice, and there's a hole in the middle, and the string attached to the block goes through the hole, and somebody under the ice pulls on the string, which means that the block will move closer. And the first question is the angular momentum of the block conserved in this case? Why or why not? So we definitely have some external forces at play, but the question remains, do they exert a torque? Because remember, the definition of, or the change of angular momentum can only be caused by a net torque acting on the object. So if you look at the box from the top, so it's like this, and it has some velocity v that direction, and the central rotation is there, so it has a position vector r. And now, when the string is being pulled, the direction of the force, or the tension force, is of course along the length of the string. So let's make this, try to make it a vector like this. And now we can calculate the torque caused by the tension. So let's call that torque by the tension force. So that's going to be R cross the tension vector or tension force. But now because R and T are aligned, their vector product is 0. The cross product is only non-zero if those two vectors have some perpendicular components, and these two don't. So in fact there is no net torque exerted on the body by pulling the string. So in that case we can say that the change in angular momentum is also 0, and angular momentum indeed is conserved. Then B, what is the new angular speed? In general, the angular momentum, or the magnitude of angular momentum for this particle is, or let's put it as a vector, so it's r cross v, and at any given point, that's the v vector there, and r. So because it's circular motion, those two are perpendicular, so the cross product will be rv times sine of the angle between the two vectors, so sine 90, which is 1, so we get just mrv, or this is not equality, we're just calculating the magnitude there, so maybe this is a better way to do this. So the magnitude of L is mrv sine 90, which is mrv. Well, let's not stop there. So because we don't know the linear velocity, but we know the angular velocity initially, so that's 1.75 radians per second, and the linear velocity is just radius times the angular velocity, so finally we get mr squared times the angular velocity. So momentum is conserved, so L1 must be equal to L2. We get m times r1 squared omega 1 squared equals, or no, omega is not squared, but then the m times r2 squared times omega 2, and so for omega 2 the mass is cancelled, so omega 2 is just omega 1 times r1 over r2 squared. So omega 1, 1.75 radians per second, and R1 over R2, so that's 0.3 meters, and R2 is just a half of that, so that's going to be 2 squared, so times 4. 4 times 1.75 is 7, so 7 radians per second is the new angular velocity when it's circling at a smaller radius. And C, find the change in kinetic energy of the block. So the kinetic energy after that's K2, it's only rotational energy of the object. So 1/2 I omega 2 squared, and this is modeled as a particle, so its moment of inertia is just m times the radius, and this case is R2 squared times omega 2 squared. So let's go and calculate value. So half times mass 0.025 kg times the radius, so 0.15 meters squared, and the angular velocity after is 7 radians per second, and we get about 13.8 times 10 to the minus 3 joules. Not a whole lot. And then same for K1, so that's going to be half times m, but now initial radius squared and initial angular speed squared, and that's going to be half times 0.025 kg times 0.3 meters squared and 1.75 radians per second squared, and the magnitude is 3.4 times 10 to the minus 3 joules. And how do we get joules? Let's check those units. So we have a kg, then we have a meter squared, and 1 over second squared. So we recognize this as a newtons times meter, which is same as joules. So we're good with that. So changing kinetic energy, delta K, so it's K2 minus K1, so, and that becomes about 13.8 minus 3.4. It's about 10 times 10 to the minus 2 joules, or 3 joules, so about 0.01 joules. Because this is positive, we did positive work on the object, and D, how much work was done. So by the conservation of energy, the work done on the object is, in this case, just the change in the kinetic energy of the object. So same amount, 0.01 joules. We neglect friction, for example, that is acting between the ice surface and the particle or the block.